I'll talk a bit about sensing today, especially geared toward autonomous driving. But before I start, I put here on the slide kind of 3 pillars that are necessary to go from where we are today to a vehicle that can drive on its own safely and in an unlimited type of scenario, including city traffic. So the first is sensing, talking about 360-degree awareness of sensors, cameras around the cars, radars and LiDARs, all the information going into computing devices and building an environmental model. Environmental model means tell me where all the moving objects are, all the obstacles, all the path delimiters like barriers, guardrails, curbs, all the drivable paths and the semantic meaning associated with each path. For example, this path is a highway path, this one is going straight, left or right. All the pavement markings, traffic signs, traffic lights, all the detailed, the rich amount of information that we human drivers are used to absorb when we do driving. So this is sensing. The next element is mapping, the ability to provide redundant information to sensing about the drivable paths. So once you locate yourself accurately inside the map, you know where the drivable paths are, and the camera tells you where the drivable paths are as well. So you get redundancy. Second, you get foresight. Once you located yourself in the map, you can see beyond sensing. You can know how the path, where the path goes to, even beyond your sensing abilities. And the third pillar is what we call driving policy. This is the answer to the question why we take driving lessons. Right? We don't take driving lessons in order to train our perception or to learn how to control a car. It's quite easy to control a car with automatic gear shift. It is to merge into traffic where there's multiple behaviors. There are other drivers. Each driver has its own behavior. Some of them drive carefully, some of them drive aggressively. And as drivers, we need to understand those behaviors in order to merge into traffic. And this is a technological problem that needs to be solved. How a robotic system can merge into traffic in a way that will feel smooth within human driving behavior. So these are the three pillars. At the CES, I spent a lot of time on the mapping pillar and the driving policy. And today, I'll talk a bit more about sensing. So I'm not going to talk about mapping. At the Q&A, we can talk about mapping. I'm not going to talk about driving policy. I'm going to focus on sensing. So when we talk about sensing, there is this new game in town, a new tool called deep learning, which is a fantastic tool that has resurfaced in the past 4 years or so. And it's being used as a very significant piece of machinery inside machine learning. And as a new tool, there's lots and lots of true elements to it, but also lots and lots of hype. And I want to spend 10 minutes to go over about 2 schools of thoughts, how this kind of technology can be used, and what would really work in autonomous driving context, and what is really hype. So the 2 schools of thought I put here, one is the end-to-end architecture, and the other one is semantic abstraction. So the end-to-end architecture talks about a situation in which we as developers don't need to put any domain expertise, we don't need to put any really smartness into understanding how to enable autonomous cars. Everything will be done automatically through data. I'll show a picture in a moment. And semantic abstraction is really the hard work of breaking a problem into its components and working on each component carefully in order to build a complete system. So let's have a look at these 2 schools of thought. The semantic abstraction would say the following. We have input video. Could be other sensors as well, but let's focus on cameras. We have input video. We have a machine which has components. Each component is a deep network, and a deep network is a deep network. We don't need to go into the details of what exactly is a deep network. We have components, these deep networks, inside, and each component is responsible for something in the process chain. A component can be responsible for detecting vehicles. Another component can be responsible for detecting pedestrians. Another component can be responsible for detecting lanes and traffic signs and traffic lights and so forth. Component, and they all work together until there is an output, and the output is the vehicle control. So you can think of a component as a deep network, and each one is trained separately using data. So how do you train separately using data? You collect a lot of data, images, and you annotate with a lot of work. Annotate these images. Where are the vehicles? Where are the pedestrians? Where are the lanes? Where are the traffic signs, traffic lights? And you use this annotation to train this block, this deep network block, to learn that particular component, to learn a component of detecting vehicles, to learn a component of detecting pedestrians, and so forth. So we're talking here about a lot of work, and there is a lot of domain expertise in knowing how to break down the huge problem of autonomous driving into its components and how to build the data required to training each component. But there is another approach, and a seemingly disruptive approach. Let's call it the end-to-end approach. And the end-to-end approach is the following. Forget about breaking the problem into its components. There is one gigantic network, one gigantic deep network, receives as input the images, and the output is the actual driving control, steering, brakes, throttle. Now, why it is disruptive? Because you don't need any domain expertise. It's simply one gigantic network. You don't need to annotate images. You simply collect data where drivers are driving their car. You collect all the data from the cameras, and the output is the actual control that the driver, the human driver, is actuating in order to drive the car. So you don't need to annotate images. Where are the pedestrians? Where are the vehicles? Where are the lanes? Where are the traffic signs? You don't need to break down the problem into its components. And you simply build a huge data center of collecting real driving data without any preparation of this data. You don't need to annotate any images. You don't need to do any preparation. You don't need any domain expertise. And this is called end-to-end. And in some domains, end-to-end has proven useful, like in voice-to-text algorithms. End-to-end proven useful. So, and this is disruptive because you don't need to know about vehicle detection. You don't need to know about pedestrian detection. You don't need to know about anything. One big network, input images come in, the driver control comes out, and you simply collect all this data and you feed it into a huge network, and all of a sudden it will learn how to drive. Okay? Now, it's not a straw man type of a model. People are actually talking about it, and you see people also kind of demonstrating these kinds of capability. And the question is whether it is possible to have an end-to-end architecture that will meet production worthiness in terms of accuracy, in terms of perfection required to have an autonomous car without making mistakes, and meet all the safety standards, because we're talking about something that is safety critical. And I'm focusing on the domain of autonomous driving, because in other domains it could be different. In the domain of autonomous driving, is it possible? Now, obviously, I want to claim that it's not possible, right? But claiming something negative, the burden of proof should be very, very high. Claiming that something is possible, so I simply need to show you that it's possible. I need to build it, and I show you that it's possible. Claiming that something is not possible is tricky, right? Because how do you know? Maybe some smart guy would come and show that it is possible. But there is something that is very, very clear and very scientific that can show that this is not possible. And in order to make the claim that something is not possible, what I need to show is that there is an exponential growth hidden inside. Exponential growth meaning that the amount of data that I'll need to collect in order to reach the same performance level as the other model would grow exponentially. Now, exponential growth is something that technology cannot handle. Linear growth, polynomial growth is something that we can handle. Once we talk about exponential growth, it's not possible to handle. No matter how many vehicles you send in to collect data, if we're talking about an exponential relationship, it's never going to happen. And then the question is, where is this exponential growth coming in? So it's all about, there are two elements here. One is, it's all about corner cases. What makes both driving assist and autonomous driving become reality is the possibility to find kind of a needle in the haystack, to find all the rare events. There are many, many rare events that needs to be covered in order to reach from, say, a 90% capability to a 100% or 99.999% capability. Building something for a demonstration, something that will drive in typical environments. I'm not saying it's easy, but it's relatively easy. It's manageable. Building something that would reach production worthiness in an automotive environment, especially if we're talking about autonomous driving, where the driver is out of the loop, requires this remaining 10%, and this remaining 10% makes all the difference. And in order to get those 10%, you need to find rare events, corner events, vehicles that are not typical in the vehicle detection, all sorts of situations of weather conditions that could cause rare events. And it's kind of finding a needle in the haystack, and it's lots and lots of work to find those corner events until you go from the 90% to the 100%. Okay, this is one of the reasons why Mobileye is dominant in the field of driving assist, because we are talking about critical safety elements like AEB. You're doing collision avoidance, the car is braking, and you don't have tolerance for mistakes. You don't have tolerance for a false positive, for braking when you're not supposed to brake, and you don't have tolerance for false negative, means when you're supposed to brake, you don't brake. And to achieve that capability, you need to go over lots and lots of corner cases. So it's all about corner cases. And the point I'm going to make is that the probability of those corner cases decreases exponentially when you're talking about this end-to-end architecture. Okay? But there's another element, and this is the importance of prior knowledge. Now, deep networks have been shown to perform very, very significant and impressive, performance in very nice and challenging domains. But what is less known is that they fail miserably on some simple problems. And understanding when they work, when they do not work, is critical when you go and build a big system. So I'll show you that as well. So let's start with the corner cases. And let's take a simple example. Let's take an ACC, adaptive cruise control. So the host car needs to maintain safe distance to the car in front. And we can think of it as comprising of two blocks. A vehicle detection block, because we need to know that there is a vehicle in front of us. And then we measure range and the time to contact to the vehicle in front of us. And then there's another block, which is the control. Decide whether to accelerate, whether to brake, slow down, or accelerate. So we can think of these two blocks. In the semantic abstraction, you have a vehicle detection block, which you trained it using a lot of data. So you have reached almost perfect vehicle detection. And then you have another block, whether you train it or it's hard-coded, which does the control. Okay? In the end-to-end architecture, it's all one block. Input images, output the control, acceleration or braking. So in this end-to-end architecture, the system doesn't know about vehicle detection. It needs to infer that implicitly. It doesn't know anything about vehicle detection. It is trained by input images, output the control. And go figure out what's going on inside, whether there's vehicle detection, not vehicle detection. That's the end-to-end approach. So now we want to focus on these corner cases. Let's call X1 the set of corner cases of the vehicle detection block. That means all the failures to detect a vehicle. Say a rare type of vehicle that the system was not trained on and it simply misses, or a false positive. All these corner cases, let's call them X1. And let's call X2 the corner cases, the failures of ACC, of the entire function, due to the failure of the vehicle detection. Now, clearly, not every failure of vehicle detection is a failure of the ACC, because it could be that the vehicle is far away, so even though the system did not detect the vehicle, it doesn't affect the ACC, it's not a failure of ACC, or there could be all sorts of control tricks to compensate for failures of vehicle detection. So not every failure of vehicle detection is a failure of ACC. Therefore, the probability of the ACC events is much, much smaller than the probability of the vehicle detection. Okay? So to make this clear, let's look at an example. Let's assume we look at this image, and we see a rare type of vehicle. It's a construction vehicle. We normally do not see these vehicles. So X1 would be, what is the probability of seeing such a vehicle anywhere on the road? And the probability is not very high, but it's not very low as well. You know, when there's construction zones and so forth, you see such vehicles. Okay, so maybe you'll see such a vehicle once every 2 days. X2 is what is the probability of an ACC failure due to a rare type of vehicle. So this requires me to drive behind this rare vehicle. What is the chances that I'll find myself driving behind a construction vehicle? Much, much lower. If X1 is once every 2 days, X2 could be once every 1 year. Okay? The point is that an end-to-end system, the corner cases that are available are only the X2. It doesn't know about vehicle detection. Okay? So what comes out of it, since this probability is much, much lower, an end-to-end ACC system will have much fewer corner cases to go on. Considerably much fewer corner cases to go on. And therefore, for a fixed amount of training data, it will be less accurate and less safe. Now, this was a toy example where we have 2 components. Let's assume that we have now a real system with many, many components. We're talking about autonomous driving. So if we have Q modules, Q components, we're talking about an exponential relationship in terms of the availability of corner cases. So if you take this around, it means that you'll need an exponential growth in the amount of data that you need to collect in order to have the same availability of corner cases in order to train your system. So the bottom line here is, from this perspective, the end-to-end system is not workable in the sense of reaching a production-worthy system. Okay, this is important. But then there's another component, and this is the prior knowledge. So when we look at deep networks, even though I didn't explain what deep networks are, it's not critical. It's not. I don't need to explain. Think of it as a black box, okay? And then look at Wikipedia. What is deep networks? Okay. So they have shown to do quite impressive, to achieve quite impressive performance on seemingly difficult problems like categorizing images, locate objects in images, face recognition, and in some cases even achieve human perception in terms of its abilities, voice to text. What is less known to the public, professionals know that, but to the public, is that simple problems cause failures to these systems. One is what is called the n-bit parity problem, multiplying numbers, simple visual tasks. So let me show you some examples. The n-bit parity, it's an old computer science problem. You have a string of bits of zeros and ones, and if there is an even number of ones, the output would be 1. If there is an odd number of ones, the output would be 0. This is called parity. So you can think of this. In 1997, there is a paper showing that you can build a neural network architecture that has 3 layers. The layer on top has n nodes as the number of bits. Then the layer below that has n divided by 2 number of nodes. And then the third layer is the output, the 0, 1 output. And the weights between the input node and the hidden layer node are hardwired. The weights between the hidden layer node and the output node, you can determine them through a system of linear equations. So there is a solution. But what is known that even though there exists weights to solve this problem, if you try to train this network using the tools we have today, using optimization techniques, it doesn't work. Beyond 30 bits, you cannot train such a network. Even if you oversubscribe this network, you put more layers, more nodes, it doesn't work. So you have here a very simple problem in which deep networks, technology of deep networks that we have today would not solve it. Let's look more recently, 2015. It's a very nice paper by Shmuel Peleg and Yedid Hoshen, where they train a network to learn addition, to learn arithmetic operations. So it's a network that receives 2 images, 2 images of numbers, and outputs their addition. And it succeeds. It's very impressive. Right? But when they try to do it on multiplication of numbers, they cannot do it. Whatever they try to do, they cannot do it. So a network simply to learn multiplication of 2 numbers, we don't know how to do it with deep networks. Right? We want to do autonomous vehicles with deep networks, but multiplying 2 numbers, we cannot do it. Okay? Go even further, 2016. Right? Yoshua Bengio. Here he takes a task where you have basic shapes, and you are creating an image. Either you are creating an image with a single shape with geometric transformations, or an image where you take multiple shapes. And the output should be whether the image contains a single shape or contains multiple shapes. Okay? So now an end-to-end system would receive an image as input, and output would be 0, 1. 0, there are multiple shapes. 1 is, it's the same shape. And a semantic abstraction would be, you have a system that first recognizes the shapes, and then you simply decide whether you have seen the same shape in the image or not. Okay? So when they do the end-to-end system, completely failed. They could not build a network architecture that will answer this question, is there a same shape in the image or not? When they abstract it into first recognize the shape and then decide whether we have the same shape or not, then it succeeds. So these are simple examples of showing that you need prior knowledge. When you take a complex problem, you need to break it down into components that you know can be trained using a deep network, and not just treat it as one big black box for the two reasons that I gave. One is the corner cases. The other one is practically not everything is trainable by a deep network. So if we now take this picture, and this is the last slide, and there's another slide. We have an input video, input image. We have a number of deep network blocks. Each one is specializing on a particular component, like vehicle detection, pedestrian detection, lanes, traffic signs, and so forth. All the stuff that we need to start gathering up from an image. And then we have other blocks, which I put here as triangles, which are not learnable blocks. For example, making measurements, doing a control, mapping from 2-dimensional to 3-dimensional coordinates, visual motions. All of these are components in the big system. Then there's another component, which is learning the driving policy, low-level control, and then you have the output. Now, when you look at what is necessary here, we split this into end-to-end and semantic abstraction, and I explained why end-to-end is not a workable solution in the context of autonomous driving, because of the corner cases and because of the many components that you need. Some of them are non-trainable by today's technology of deep networks. You look at semantic abstraction, there is two things. One is domain expertise, understanding the domain of automotive and what goes into building an environmental model. And the other one is prior knowledge. When you look at the prior knowledge, there is classical machine learning elements, what's called bias variance, making sure that you don't overfit and you have a low approximation error. But in deep networks, there's another element which we call computational complexity, which is when can you train a network and when you cannot train a network. So high computational complexity means that it's very, very difficult to train that network. Low computational complexity means that it is easy to train that network. So for example, the example that I gave with the n parity problem, even though it's very, very simple, has a very high computational complexity because we don't know how to train it. Okay? So when you decompose your problem into pieces, you have to know about this. And then comes the domain expertise, is defining the modules, which model does what and their interconnections, the tool chains and all the safety modules. With the tool chains, there's a lot of effort of annotating images. For example, at Mobileye, we have more than 600 people annotating images. And this is rapidly growing. By the end of this year, it's going to be about 1,000 people. There's all sorts of methodologies of hunting for rare events, for using active learning, for using both annotated images and non-annotated images in a clever way. There's a tool chain that evolves over a long period of time. You bump into many, many problems, and using this bumping into problems, you refine your tool chain. And this is part of a domain expertise that sometimes is a bit overlooked and undervalued. Okay, so that was kind of 20 minutes of trying to put some perspective into the field. What is this new tool of deep learning and its limitations? Now let's go into what we do. How do we break up the sensing problem into its components? So when you look at an environmental model, there are three pieces that go into it. And I'm putting these pieces in increasing complexity. So the first is the easiest one, next is more complicated, the third one is really the killer. That's really, really challenging. So the first one is detecting moving objects, moving and stationary objects. So detecting vehicles, pedestrians, obstacles, kind of non-model-based general objects. You need to achieve 0 false negative, achieve 0 false positive. You need to, for example, with vehicles, you need to detect them at any angle, not only when their rear is visible, and you need to detect also general obstacles. Okay? So this is a natural growth of driving assist. I'm not saying it's easy, but it's a natural growth of driving assist. We're not talking about leaps. We're talking about an incremental growth, going from the current state of vehicle detection to a more complicated vehicle detection where you have any angle detection and achieve zero false negative, zero false positive. The next one is path delimiters. There is a free space where you can drive and where you cannot drive, and the edges of the free space, you need to know what is there. Is it a row of parked cars? Is it a curb? Is it a barrier, a guardrail? So these are called path delimiters, and detect any boundary is part of that, and label the types of boundaries. So I would say that this is the first leap beyond driving assist, but it's already starting to be included in driving assist. For example, the Tesla Autopilot has many of these components. The 2018 Euro NCAP requirements have many of these components, like the any boundary. So this is the next driving assist. Okay? The drivable path is the biggest step. Because if you think what is really needed for enabling autonomous driving, it's not detecting other vehicles and making sure that we don't collide with other vehicles. That technology is ready more or less today. It is understanding the roadway at the details like human drivers, understanding where all the drivable paths are, the semantic meaning associated with each drivable path, reading the pavement markings, understanding based on the behavior of other vehicles which path I can drive, which path I cannot drive. Like I see oncoming vehicles, I know that this path is a path that is not, it's a non-drivable path. I read pavement markings, I know that this is a highway exit. I associate also information about paths by looking at traffic signs. I know that there's going to be a merge point 200 meters away because I saw a traffic sign telling me about that. So it becomes, there's a lot of intelligence needed in order to understand, to map all the drivable paths. And this is the next leap. This is a very challenging leap. And this is the missing link between driving assist and autonomous driving. Autonomous driving is not about not colliding with other vehicles. That exists today. That's not really the big challenge. Autonomous driving is not knowing about pedestrians, whether the pedestrian is looking at me, whether it's not looking at me, whether the pedestrian is on the sidewalk or pedestrian is not on the sidewalk, whether the pedestrian is waving his hand, all what you see in clips shown by other companies. That is nothing. That exists today. The real challenge is understanding the roadway. Think about not highway, even in highway it's complicated, but think about city traffic. That's where the big challenge is. And here we need strong sensing that can provide that information, and in addition, maps. The map gives us a redundancy. So in terms of redundancy, we're talking about redundancy. We need redundancy in everything we do. So for moving objects, it's radars and LiDARs that gives us a redundancy. For path delimiters, we're talking a map gives us a redundancy. In some cases, a LiDAR tells us a bit information about path delimiters. And redundancy for drivable path, the only sensor that can sense drivable path is a sensor that is sensitive to texture, and that's only a camera. So the only other sensor that can give me a redundancy is a map. This is why maps are so critical in our space. So let's look at a few examples. So this is the vehicle detection that is required going forward. So you see that there is a three-dimensional box around each vehicle where the system knows to associate not only the fact that there is a vehicle and put a three-dimensional bounding box around it, but to know that this is the left side, right side, front, rear of a vehicle, and do it in complex scenarios like what you see here, and of course at very, very high accuracy at weather conditions, and reach near perfection in the ability to detect these kinds of scenarios. Here's another example. You see the complexity of city traffic, right? The need for detecting vehicles at all angles is something that goes beyond ADAS today. Okay? Then comes the path delimiter. So understanding what is the path delimiter, we can look at this clip. I'll stop it here at some place. So what we see here, we see a kind of a green carpet. The green carpet gives us the boundary of our free space. And then at the edges of the green carpet, we provide a category of what that edge is. Is that edge a row of parked cars? Is that edge a curb? Is that edge a barrier, guardrail, and so forth? We have about 15 different categories. And the system, it's a deep network component that learns associated images with the output that you see here, with the complete free space and labeling the boundaries of the free space. We call that semantic free space. Here we see this from a 360 degree. We have about 8 cameras. I'm showing here only 6, but we have 8 cameras around the car. And the system provides both the free space and the boundaries on the free space and all the moving objects. Okay. The last component is the drivable paths. And drivable paths, there are a number of components that need to be developed here. First, there are paths that are not defined by their lane markings. Yet humans can navigate, understanding how the free space is structured and knowing that this free space is basically 3 lanes and they drive along the right lane even though there are no lane markings. And what we do, we in order to reach a high precision ability, we fuse many sources of information. For example, we have a module that does lane detection, the classical lane detection. We have the model of what you saw, this is called holistic path planning, trying to predict a path without seeing lanes. We have the semantic free space, and we have other modules that are all fused with another deep network component to bring us the lanes in high accuracy. So let me show you an example of how this looks like. The point here is to focus on the red line here, or the center. So the red is the fused information, and all the rest are building blocks. So this magenta is the holistic path planning, for example. And what you see here is that the red lines are very, very stable, and we're talking about very challenging conditions. When you're inside a tunnel, the road is wet. So it's a combination of very adverse conditions. In a tunnel, the road is wet, you can hardly see the lanes, and you want to do control. You want to laterally control the vehicle, right? Let me show you another situation. Here again, focus on the red line. The red line is really stable, and you don't see the lanes here. These are the kinds of situations where you still want to enable lateral control, because otherwise you'll not have autonomous driving. Autonomous driving the challenge here is not to enable autonomous driving in clearly marked roads. That's not the challenge. The challenge is to go to these kinds of areas and do it. I put here a clip from the Tesla Autopilot, which has some subset of these capabilities. And this is something I downloaded from the internet, and let's have a look at it.
Right now, autopilot is in full effect. Once autopilot is engaged, it first reads the lines, then it follows the cars. That's how it gets you from point A to point B while handling all the curves and turns along the way. Okay, so let's stop it here. So you clearly see that the woman here is driving without touching the steering wheel. What I think is interesting here to see is when you look outside, you don't see the lanes. It's very low sun with shadows and so forth. This is a very, very difficult conditions for enabling lateral control. There is a lead vehicle in front, but the system will not rely only on a lead vehicle in doing lateral control. It needs to get some information about the lane sensing. And the ability to do lateral control in this kind of situation comes from the kinds of components that I mentioned before. Because one of the big successes of the Tesla Autopilot in terms of the ability to do hands-free driving comes from these types of technological components. But this is only the beginning. If you look at really what's going on in understanding the road, there are what we call semantic points. It's better just to show pictures of it. Now, these kinds of areas, they give a lot of information about what's happening. For example, here there's a highway exit, there is a split. So there's about 15 different semantic points, categories that once we find them, and I'm going to flip through these images. Once we find them, we're getting a sense of what's happening in the road structure. And again, finding these points, it's a building block. It's a deep network component that takes an image and maps it into the semantic points. And then you take all the lane sensing algorithms, you put them on top of those semantic points, and then you start getting a sense of what's happening in the road. I said this is the most complex part of achieving autonomous driving. It's not the moving objects, it is this, okay? Okay, so this is this component. So
that was my last slide. What I focused here was on the sensing. What are the building blocks of enabling the sensing? But I started the first 10, 15 minutes in trying to put a bit perspective on how to achieve autonomy. Right? There are new tools, but you have to take these new tools in a certain grain of salt. You know, not everything. People tend to overreach in their claims of what one can do with the new tools, and I try to provide a perspective, but grounding it in an articulated manner, not just saying what is possible and what is not possible. Explain why something is not possible, and that was the example of the corner events, the corner cases that I mentioned, and also the prior knowledge. Of course, there's the mapping and the driving policy, which are huge pillars in what we do, but I talked about that at the CES event. Of course, the Q&A, you can ask about it, and I'll be happy to answer. Thank you.